Hello and welcome. My name is Tim Sarowitz. I'm the VP of Education for the Linux Foundation, which means I get to do some exciting stuff like webinars with some outstanding people in technology. Today, I'm joined by Gianmarco Iodice and Ashok Bhatt to talk about Gen AI inference on CPUs and some of the very cool technology and open source project that is associated with it. Gianmarco, Ashok, would you like to say hello and introduce yourself real quick to the webinar?
Absolutely, and thanks a lot, Tim, for hosting this webinar. I'm Gianmarco, and I'm leading the engineering team at Arm for GenAI. It is a very interesting position right now because I'm looking at use cases, frameworks for this hot topic like GenAI that we're gonna listen quite a lot today. So.
Hello, everybody. I'm Ashok Bhatt. I'm part of the product management team in the cloud business of Arm. And in our segment, we look at what we call the cloud to edge. And it's quite interesting how the LLMs of various sizes are being created, tuned, and changed to fit to edge and the cloud. So we'll talk a lot about that today.
Sounds great. I'm looking forward to it. So the title of the webinar is about unlocking power and speed of Gen AI inference on CPUs. You guys are the experts in the field. What is inference when we're talking about Gen AI?
Okay, so probably I can start and Asha can absolutely follow up. So when we talk about inference, in short, we are talking about the model execution when you have already trained as something to perform a specific task. In the context of generative AI, we usually refer to models that are capable to generate new media contents. For instance, they can generate text, can generate audio, can generate video. And so when we talk about inference, we're talking about a model has been already trained, and we are considering just the model for performing that specific task. Is there something else you want to add, Ashok, on top of this?
I mean, the typical way to understand is training is when a model learns and whatever it learns gets applied during inference. So inference happens many millions of times. If you think about ChatGPT, every time you type a query, inference is happening. Training is when OpenAI folks took all the data and created the ChatGPT model. So they did it once, and we can use it many times. So the many times is the inference, and typically it's expected that the amount of compute energy that is spent on inference over the life cycle of a model will be more than the amount and time and energy spent for training.
That makes sense. That makes sense. Yeah. So to kind of recap, then the training is kind of somebody's education, how much time you spend in school, and then inference is kind of the thinking phase where you're applying it when somebody asks you a question like, what's the capital of Texas? And then you're like, I don't know. Did I learn that in school? And then you can draw from your knowledge and what the question is. Okay, that's pretty neat. I think we have our first poll question rolling up so that we can interact with the audience here a little bit. I'll read it out loud to help. Which aspect of ML inference do you find most challenging? And you can choose a single choice from that. We'll give folks a couple minutes to click on that and make their choice. And then we'll look at the results here in a couple minutes and talk about that. It's always interesting because when people sign up for a webinar, how much do they know ahead of time? At the Linux Foundation, we talk to a wide range of people from first day to subject matter experts. So this is always kind of interesting for me as a host for this. So with what we're talking about here is inference, and you mentioned power and cooling. That's not only money, but it's also the biggest challenge in every data center that is out there. That's what you build for nowadays is power and cooling. So what degree are we talking about of benefit, and what makes it better or worse? Like we're talking about Kleidi, and we're talking about some of the things that ARM does. ARM is everywhere from mobile devices to the data center. It's probably more places than people even realize. So what does Kleidi do for us? And why should we, like, what is it and why should I care?
So Ashok,
I'll give the high level 30,000 foot view, and then Gianmarco will, I guess, can go into the details of it. So over time, since maybe last 10, 15 years, all CPUs, right? I'm not talking about just ARM CPU here. All CPUs have been adding extra features to help with machine learning kind of workloads. You would have heard about, in the case of Intel, they have a vector unit and it's AVX12, AVX512, AVX2. Recently, they added something called AMX. The ARM guys, we have added bfloat 16 support, wide vector unit, and all of this, right? Now, this is what the hardware is doing to make ML happen fast, inference especially happen fast. But the hardware alone is not the complete solution. Most people use high level software. And how does the high level software benefit from the low level hardware improvements? And that's where you have different solutions depending on different architectures. In Intel, they have something called one DNN and one API that helps you get the best of the hardware. In case of us, we've introduced something called Clyde, and I'll let Mr. Gianmarco uh, go into more details because he's the brain behind most of it.
oh, thanks, and too kind. And by the way, I think this question comes at the right time, also in light of what I'm seeing on the poll results, because when we talk about Clyde AI, we're talking about performance optimization, which is absolutely the key aspect. So, but let me start from what developers have to do to run these models. So we're talking about model inference. And when we talk about model inference, of course, you are talking about AI frameworks. Okay, so Ashok mentioned already some AI frameworks, and out there are many options, and developers have many options to run these models. What's the biggest challenge? Getting the best performance, because if we get the best performance, we can also minimize the energy consumption, which is probably one of the most important things, right? Let's keep it short, the execution time, in order to minimize the energy consumption. So what did we do with Clyde AI? So we decided to create a new library, a library for the ARM CPU that provides the highly optimized operators for only for those that are critical for the AI workloads. What does it mean? An AI workload in general is made of different operations, right? So you need to run sequentially as different ops, but not all of them are critical for getting the best performance. So a Clyde AI then is a collection of the critical operations required to run very efficiently these models on the ARM CPU. And this actually also brings to the benefit of the CPU, because when we talk about the CPU, you also have this flexibility to focus only where it matters. You don't need to optimize everything. Of course, everything is important, but certainly if you focus on the critical ops, you can get the biggest gain basically very easily. Hopefully, I have explained what it is, Clyde AI.
No,
What we
it's a great.
do, sorry, Tim, go ahead.
No, go ahead, Ashok.
I think what we do is once we have these optimized microkernels, as we call it, we work with all the framework teams, and this is not unique to ARM. Even Intel folks work with all the upstream open source frameworks, and we try to get these optimizations in them so that you, as a user, if you're using PyTorch, TensorFlow, XNN, I mean TF Lite, anything on the mobile framework, then you don't have to worry, right? It's just whatever the hardware can provide, it just magically appears as performance and energy saved for you.
Yeah, and certainly this is absolutely very important to mention, and thanks Ashok to actually to say that, because this library is for AI framework developers in particular. So the vision is that the third-party developers that they want to build their application on top of these models, they basically don't need to consider all the dependencies because these optimizations are already integrated in these AI frameworks.
That makes sense. So, I'm professionally ignorant, so I ask dumb questions well. It's how I hide not knowing. But, I've from my understanding of AI, I need a GPU for all things. What's different? Why is that still true? Why is it not true anymore? Like, educate me in why GPUs aren't the entirety of AI.
I'll go
Asher?
first. Okay.
Nobody wants to answer my question.
So I think it's very interesting, the journey of a GPU. So 10, 15 years ago, when AlexNet was first deployed, I think what it did was people successfully used GPU, especially the CUDA interface, to be able to train and produce a model that bet state of the art by a big margin, right? So since then, training has almost always been associated with the GPU because you need that level of compute, you need that level of interconnect and all of that, right? So even today, when OpenAI does ChatGPT model or our friends at Meta do Llama model, for them GPU is super important, or accelerator to that extent is super important. Now, when it comes to inference, unlike training, it happens everywhere. It happens on your phone, it happens on your microcontroller, it happens on your laptop, it happens in cloud data centers, and so on. And not all of these places have GPU, right? Your mobile will have some GPU, like ARM provides Mali GPU, has Qualcomm GPU. There is, I think Apple has its own GPU and so on. But then microcontrollers they may not have anything. In cloud, usually what happens is it's disaggregated, which means mostly the CPUs are provided separately. If you want a GPU, then it becomes a CPU plus GPU option. It's usually more expensive. So as a result, an inference workload, what model developers have done is they have taken the master workload that gets trained on a fancy GPU, right, spending millions of dollars. They distill it down and produce a lower complexity model so that they can run on devices which don't have that much of capability. As an example, if you think about Llama model, there's a 405 billion model that is the kind of the best model that you can get. 405 billion is the number of parameters. And then there is a 70 billion parameter model, which is like a medium size. And then there is 7 billion or 8 billion parameter model, which is the smallest size, right? So typically the 7 and 8 billion is aimed at devices like CPU centric. You think about cloud having a CPU availability or a mobile having a CPU because it's easily can run that. In fact, if you have time, we'll show you a demo where we can do a quite fast chatbot on a 92 core CPU system. So that's the thing. So what is typically happening today in the market is if you want to run the 405 billion model, and if you if you have the kind of traffic to keep the GPU fully occupied, then that happens on a GPU. But if it's not, or if it's a smaller model like 7 billion, in fact, Alibaba has LLM models which are sub 1 billion, there's a half billion model and so on. Then those things can happily run on your laptops, can run on your mobile phones, can run on your small cloud instances with 16 core, 8 core. And a lot of it is due to the software optimizations and the hardware features that we talked about. In our case, the Clyde helps a lot. In Intel's case, whatever they do with one API helps a lot. Gianmarco, you want to add?
Yes, I can also add some technical aspects, right? So when we are talking about GPUs, most of the time I hear the following sentence: "Oh, we use the GPU because this is a workload that we can parallelize very well. That is the reason I use the GPU." That is probably the wrong answer. It's not because we can parallelize the workload. It's maybe because it has more compute power, okay, to make the model running faster. But compute power is not the only thing that we need to consider because we need to consider also the efficiency. How big needs to be the workload to be very efficient, right? And Ashok actually mentioned a very good point. The more compute capabilities you add to the hardware, and of course, the biggest has to be the workload. So if you consider I'm not very, but small model, well, small is very relative, but in this context, but if you're talking about 4 billion, 8 billion models, this can run very well on CPU and in some cases also much more efficiently. The other aspect mentioned by Ashok is, well, the GPU for sure is available on infra, but in some contexts, the GPU might not be available as well. But hopefully I gave you a bit
Oh,
of.
yeah, it's funny because I would have answered the same way that you said I shouldn't. So this I've learned something now, and always a good thing. Well, in that case, how do you balance the use of CPUs and other accelerators, your GPUs, your TPUs in your workflow?
That's a very good question. So I would answer in this way. It does not exist a single solution that fits them all, right? So it truly depends on what applications you are targeting. It truly depends on the requirements you have, the workload size as well. Let's consider mobile, an application on mobile, an application that you're trying to leverage with AI. Well, that application could run during a game, so the GPU could be busy to do operations required for the game. So might be not an option, and you need to run on CPU. Or you could have a scenario where actually you cannot use a CPU because the CPU is busy on doing something else. And you need to run on a different axis. So what I'm trying to say truly depends on what you need to achieve and how. There are also scenarios where you need very instant response, right? I give you a very simple example. These models are usually very large and they occupy, I mean, a big chunk of DRAM, okay? When these models are not used, of course, we don't want these models to reside in memory, right? But in some scenarios, you want to run these models very quickly because the user asks me to turn it on and needs to go in DRAM very quickly. So in these scenarios, for instance, the CPU can be your friendly IP because you can move from the storage to the RAM very quickly and you can start the execution very promptly compared maybe to other accelerators. What I'm trying to say is it truly depends on what you're trying to target. Ashok.
I can add a typical workflow that we hear from cloud customers. So there are two kinds of customers that we hear. One is they prototype quickly, and when they prototype, they use whatever the fanciest, most expensive hardware they can get hold of. So if they can get hold of the latest GPU, they'll do a latest GPU. If they can get hold of the latest TPU, they'll do it because they want to do a proof of concept, right? So they'll do a proof of concept. And then when it gets to the deployment, that's when they start measuring what is my like inference per dollar cost, right? How many inferences can I do per dollar spent? And typically, this is quite easy to do it in a cloud because you'll have, let's take an Amazon case, you'll have an EC2 instance with various CPU options, with various GPU options, and so on. So there are best practices, and what typically happens is if they think, oh, this is too much money being spent on a GPU, then they'll try to see, oh, can I try a CPU, or can I try in some cases a CPU? So one example I've seen is when they want quick response, immediate response, real-time response for a large model, they end up having a GPU standby and you quickly get the response. Sometimes, in other cases where they have to do an offline processing, typically you would think offline GPU is better, but this company had a whole bunch of CPUs available and they had a lean period, right? If you think of an e-commerce company, nothing much happens in the night. So they had a lean period, and during those lean period, they used the CPUs to run even 70 billion parameter LLM model. So that is one workflow. The other workflow I see is users start with their existing application. So there's an application that already runs on an EC2 instance. Typically, it's all CPU. They try to run it and they find that, oh, I have added this ML workload to my application and I'm facing performance issues. So what do? You have 16 core, now you try to have 32 core. Okay, that's not enough. Then you go to 64 core. Even that's not enough. You try to change the model. You try to do quantization or other things. There might come a point where, oh no, the compute that's available is not enough. So let me switch to a CPU plus GPU instance, right? So that's how they do. So we have seen both. The well capitalized large companies start from GPU first and then go down. Whereas a lot of research organizations which have an existing, they start with the CPU and then try to move to a GPU or a TPU.
That makes sense to me. We have a question from the people attending, and I'll just read it to you guys. It depends on where the inference is processed, right? In case of AI like ChatGPT, inference is happening in SaaS, no matter what resources we have locally. If system is hosted locally, then resources matter. So does it really matter where, I guess not, does it
It's
matter
an
where it's
important
being
point, right?
processed?
It's an important point. Let's think about I start a ChatGPT service today. And if I don't have the necessary load so that I can keep like a swarm of GPUs fully loaded, then it'll be very expensive. So if I have a GPU and if I'm just using it to serve one or two, right? On the other hand, if I am something like OpenAI, where I'm getting millions of requests at every point, they can batch it and they can make sure that the GPUs are fully loaded. The best way to think about a CPU versus GPU story is think about you have two planes, a A380 and a small plane, okay, or a car, and you want to go from A to B. So if you can fill the A380, that is the cheapest way for you to go from A to B. If it cannot fill a A380, then if you just have like 10 seats filled for 380, then it might be one of the very, very expensive options. So it kind of matters for OpenAI when they are doing their resource management. On the other hand, if you take your point, one of the things that a lot of companies are doing, I hear even Zoom is trying to do, is they're trying to do some of these inferences on your local laptop so that they can kind of do some of the processing locally and then do more processing in things. So it may not be not applicable for a chat GPT kind of thing. But if you think about this conference and there's an AI ML workload trying to improve how the video looks or how the audio sounds, a lot of it is actually happening on your laptop. So that's where kind of resourcing matters. And what is available on a CPU and or what is available on the laptop, CPU plus GPU plus whatever else. How do you make optimal use of it?
Okay, that makes sense. Well, this is probably a good time for our second poll question then. I kind of think it leads into it. So this question is, have you ever considered running your ML model on a CPU? And you have a yes or no choice. While people are clicking on their answer, it's a question that with so many different types of systems out there, I have my phone and I have I have a Mac, I have an Intel box, I have an ARM-based system. Does it matter? Like, how would I know which one is optimal for my workload? How do I get into that? We had a question a bit ago about does having a unified GPU like Apple in the new Macs make a difference? And is it better or worse for separate ASICs in the data center? Like, how do I know other than running a test? Is there a way of knowing this?
Well,
It's
sir.
it's a yeah, it's a
No,
million dollar question. Go ahead, John. Yeah.
no. You started.
Okay, so this is how it typically works, right? As you move away from the cloud, something called aggregation happens. Now, what do I mean by that? As you go towards your phone, people err on the side of having extra hardware. So they will have a GPU, they'll have an NPU, they'll have a CPU, they'll have many CPUs and so on. And the idea being, we don't know what applications will run 2, 3 years from now. We don't want to kind of be found wanting because we didn't provide hardware 3 years ago, right? So that's how it works on the. So there, have an integrated GPU or any amount of capability that you can put on a mobile or an edge device is brilliant, right? You don't want your router to be changed for next 10 years, and it should be future proof in terms of ML for next 10 years. And that's a tall order. You go to the cloud, it's complete opposite. So they want to do what is called disaggregation. What do I mean by that? They want to keep CPU separate, GPU separate. If they can keep, they can keep memory separate, storage separate, because all of them can be independently upgraded. So there, the risk is if you do, let's say, a CPU plus GPU option or an integrated GPU option, and you deploy in the fleet today, the base case that it should satisfy is it should take care of the next 3, 4 years, and I should be able to sell it to my customers for the next 3-4 years for at least, because that's how long they keep. And that's where they're very careful because they deploy in multiple centers, right? If a specialist hardware gets deployed and it doesn't get used, it's wastage of real estate, I mean, power, everything. So they're very, very careful. They typically go with disaggregators. So they'll keep GPU separate, they'll keep CPU separate, they'll keep specialist accelerators separate, and so on.
Okay.
I
And
can
that,
probably
which,
add how it works on mobile if you want. I mean, this is a usual problem for app developers, right? They have in front of them how many options? Many options, and your app has to run on all phones. What they usually do, they consider the worst case scenario, they profile there, okay? And if the performance are good, for sure, what you're gonna see after that phone, so the generation after that phone, will be essentially faster, and this is usually the approach. And here, the CPU is very, very important because the fact that, in particular, ARM is everywhere on mobile makes everything a lot easier, right? Because this means that the complexity will be held by the library. The library will detect at runtime what features are available in hardware and will dispatch the proper the proper operators optimized for that particular hardware. But
okay.
from an app developer perspective, they usually consider the worst case scenario. If that works, it will work
Right.
also.
We all tend to do that in our work life is what's the worst case? Let's take care of that first and then go towards optimization. I think the poll results are in, so let's take a quick look at the poll results. So we see 79% have said yes, they have considered it, and 21% say no. So what's is that what you expected to see from our audience?
I would have expected other way around. I would have expected 21% want to run CPU and 79% run too. I mean, I guess maybe the title of this webinar may have biased our audience, but it's great to see. I mean, so many people want to run things on CPU. Yeah, in whatever way we can help you, we are there.
Absolutely, absolutely. And we had some other questions about the kind of go together as far as and I'll read the questions to you, and then I have my own to add to it at the third. So one of the questions is we can inference of SLMs and CPU, but it takes a lot of time to reduce output. Do you have tricks or ideas to reduce latency? That's one question. The other one is a hypothetical. Do you see new math replacing the current brute force math, produce the vector embeddings and so forth, with the goal of reducing or eliminating the need for massive hardware to create and run AI models? And that then leads into my own question that is having to do with what's your trips? What are your tricks or ideas for optimization? What are your optimization techniques that will improve this performance that you can share with us?
Yes, probably I can say something on this topic. And this is also based on what we have seen in the last couple of years, many developers playing with quantization techniques. So these models are huge sometimes, very big compared definitely to AI models that we saw before generative AI. We're talking about models with 4 billion parameters. And if we consider, let's say, FP16 or integer 8, let's say integer 8 computation, this means that you need 4 gigabytes of RAM. And on mobile, it's quite a lot. Therefore, the most important technique here is the quantization using lower numerical precision. And with lower, I mean 4-bit quantization, for instance. But the community is also playing with integer 2 or something between integer 2 and integer 1. So 1 bit and 2 bits per value, which is quite fascinating. And the community actually proved the benefit. This is, in my opinion, the most important technique, and when actually the CPU can provide the greatest benefit because of the why the data types support, because we can support all the data types, including BF16, for instance, that can help to save space for dequantization parameters, but also because of dedicated instructions that can accelerate these quantization techniques very easily. Ashok.
Yeah, so I'll give you a stepwise thing as to what can help, right? The first thing is not all software frameworks are equally fast. So if you want to run it on a CPU, typically you will find the Llama CPP is super fast as compared to traditional frameworks, right? If you think about PyTorch, I mean, they're all trying to catch up, but and so knowing which framework is most optimal for your target hardware helps. And there are a few candidates. You have Llama CPP, you have PyTorch, you have JAX, you have so on, right? So today, Llama CPP is one of the advanced ones. So that's one thing. The second one is the SLM itself, right? Do you need 7B or can you use Quen instead, which is smaller and so on? So that will, if you reduce the model size and if your output is still acceptable, typically that straight away improves your performance. So it's like, think about there's so many variants of the models. Do you really need the model that you're looking for? And the third one is what John Merker said is the quantizations. Every model, you can run it in different modes. You can run it in full 32-bit mode. You can run it with, in at least in ARM, you can run it in bfloat 16 under the hood mode or bfloat 16 itself, int8, int4. Again, every step has a cost. So your performance might improve. At the same time, some quality degradation might happen. You'll have to see, try it for your data set and see which one works best, right? It's the same true for GPU, same for it. The last one is depends on what hardware you have. So if you're in a cloud, obviously you can try and going from 8 cores to 16 cores to more. If you're going in a like there are different generations of CPUs out there, right? In the case of Intel, if you go with one with AMX, it's going to be faster than one without. In case of ARM, if you go one with the original generation of Graviton, for example, that didn't have certain ML features, you upgrade to Graviton 3 or 4, you'll suddenly get more value, right? More performance. So typically, software, model, quantization techniques, and the hardware that you pick, all four contribute to performance. And I would like you to try various variants and see what works best.
That makes sense. Yeah, it's, I don't try to make stuff basic for myself. It's like a race car. Is it my tires? Is it the engine? Is it the
Yeah.
body shape? Which one is it? Well, it's all of them to some extent. And you don't really know until you're going around the track on that day what the
Yeah.
fastest car is going to be.
Today, the state of the art, both on ARM and Intel in CPU, is frameworks. Usually, Llama CPP is super fast. That's kind of gives the best. In terms of models for a typical chat application, 7B, 8B, depending on Gemma, it's like 2, 3B. I mean, anything 0 to 8B, those are decent, right? They give the best performance. And if you want to use quantization on ARM, and I guess even Intel recently, 4-bit quantization is considered good enough. So there's something called perplexity score. So that's kind of decides the quality of the outcome. And for 4-bit, we have seen that for chat outcomes, it's really good. So you can just go with 4-bit. The 1-bit and the 2-bit are still in experimental phase. I don't think it's in production phase. Um, all hardware vendors are not sitting tight, right? I think there's an FP8 that's going to come soon and so on. But today, the 4-bit LUM CPP, something like 1 to 8 billion model, and usually memory matters than number of cores. So if you can find an instance which has more memory, then that usually helps. So if you have the same number of 16 cores, but if you can find an instance which has more memory per core, then GenAI, that's usually where you get best performance.
Okay.
By the way,
Go
Tim,
ahead.
when we talk about 8B, 4B, we refer to the number of trainable parameters just to keep it very simple for these models. So if you're talking about 8B, it means 8 billion parameters. So it's quite a lot if you consider, for instance, a floating point 32 or floating point 16 as a data type.
That makes sense. Yeah. We have another question from the audience. We have several, but one that I think ties into this. How do the number of cores and type of ALU or DSP on a CPU improve AI performance to power consumption ratio?
Okay, that's a very interesting, difficult question. So what I usually say, is it really power or is it energy here? Because sometimes we refer to power, right? But actually what we mean here is probably the energy consumption, because what we're trying to do is basically to perform more in order to minimize the time of execution. If you reduce the time of execution, you reduce the energy consumption, and the battery life will be certainly longer. So I can talk, for instance, for the ARM CPU, and so because there are some dedicated instructions for doing digital signal processing or for AI workloads in particular, and these instructions help a lot. Help a lot to minimize the latency. I can give you two examples. One is called the dot product extension, which is an instruction that performs the dot product between two vectors. And the other one is called I8MM, or is a matmul extension for CPU that provides that allows actually to perform a tiny matrix multiplication. And if you use this tiny for performing larger matrix multiplication, you can see a significant performance benefit. What's the beauty of this is that all of these interesting features are available in the cloud and on mobile as well. So if you basically have the possibility to run on mobile, it will certainly run also in the cloud, and probably even faster because you have more compute capabilities there. Asher, do you want to add something else?
When it comes to cloud, it's very difficult to find out about energy consumption. So because it's only the cloud guys know how efficient and not efficient it is. But typically, the size of the accelerator matters. So if I have a CPU which occupies certain area on the device, and if I have an accelerator which is equally big, if I use both, and you would typically end up using twice the power, right? Twice the energy. So a lot of the times it comes down to, if you can quickly finish the work, go to an accelerator, finish it, and come back. If you're not going to use the accelerator for a long time, setting up, bringing it up, then keeping it alive, and then tearing it down, those have its own energy costs. It might be cheaper for you to just do it on a CPU. So a fully loaded, I mean, think of it this way. If there's a specialist accelerator, and if you can keep it 100% loaded, that gives you the best performance per dollar, sometimes even the best energy efficiency, because it's designed for that use case, right? It's like use a particular machine that's been designed for a particular use case. The challenge happens is, I have an A380 plane and I only have 10 seats filled. That's the usual problem, right? So the best way to think about your problem is think about the airplane and seats. How does an extra seat add to fuel consumption? Usually, once you've decided on the plane configuration, it doesn't matter much. But if you want to use different configurations, that's when it matters, right? And the challenge typically people face is, in cloud, you have various sizes. You can do 4 cores, 8 cores, 16 cores, and more. In mobile, you have like low-end phones, high-end phones, and stuff. So that's where the challenge is.
Okay. No, that makes sense. And we've gotten somewhat deep into the technical information, which I love. I mean, I can geek out about this for days. But
Yeah.
bringing it back up a little higher level, we have our third poll question. So if we can bring that up, and we'll learn a little bit from our audience. Which ML framework do you primarily use? Single choice, TensorFlow, PyTorch. Of course, PyTorch is a Linux Foundation project, so I'm sure everybody's going to choose that. Onyx or other. So we'll give them a chance to fill that out. While the audience is filling out what their ML framework is, I have a question. AI ML, yes, it's everywhere, but obviously you both have been working in this field for a long time. So how did you first get involved in machine learning? And for somebody who's new, that this is, they want to get into it, what's your advice if you're starting out? How do I get into this space?
I'll go first, and John Marco will have more exciting answer. Okay. So I got introduced into the world of AI around 2017, 18. And the reason is our hardware added an AI feature. And I was in a software product management, and our management said, now that we have the hardware feature, make sure the software can use it, right? So we had to go figure out, okay, what are the latest frameworks? What are the latest software? What things run, and how do you make it happen? So we have come from the bottom up approach. The most important thing for all of us to realize is none of this existed in 2011. I think all of this started in 2012. So the entire field of AI is at most 14, 15 years old as we know the modern AI. So this is when the AlexNet, I think, was the first used in winning an ImageNet competition. And my personal experience of being on top of is very hard, but there are simple things you can do, which is use the latest models, Hugging Face. A lot of them try what they do. If you want to get next level detail, there are some excellent teachers in the internet, Mr. Karpathy being one of them, right? Andre Karpathy. He has this awesome video, I think a 3 hour video of how LLMs actually work, right? That will, that, I mean, and in a way he explains that anybody can understand. You need a very little base level knowledge. And the other thing you can do is do a simple project of train to identify handwriting. That's what I started with. Right? It's a simple thing you can train on a CPU. Do inference, try different frameworks, see the performance difference yourself. You'll be surprised how wide is the variation, right? That's how I found the best way to keep on top of this. Attending conferences, webinars, these will give you the direction to go, but it's like taking the horse to water. You have to drink it yourself to see it. And it's super helpful community. Everyone is new. Like I said, the most expert only is 13, 14 years of experience, right? They're all young people. So you get a lot of support in the community as well. So make use of it. John Marco?
Yes. So, well, I have been lucky enough to join ARM in 2013 uh, and always work on AI from the very beginning. But it wasn't the AI we're seeing right now. Before that, why I'm saying this, because all the open source contribution that we're seeing now were not available before, certainly AlexNet or 2013 in general. That period of time, as I said, I was very lucky to join ARM to start deploying the first models on mobile phones. It was super exciting. But before that was extremely complicated to join this field because you had to go certainly uni, solid mathematical background, no many AI frameworks open source. Some of them were closed source with very limited support. Nowadays is completely opposite. So there are languages that make everything a lot easier, like Python, just to give an example. There are AI frameworks completely open source, models which are completely open source, and that is probably the reason why this is a fascinating world, because we can learn also very quickly. We can learn very quickly. I believe that university for sure helps a lot in this field. You need at least a minimum background. And probably my recommendation is to have an overview, not just of the model deployment, but also what happens under the hood. Because most of the architecture we're seeing out there are influenced by the hardware they're going to deploy these models. And by knowing the hardware, you will for sure implement a model that will run very efficiently in your application. Working on both is for me probably the most interesting and fascinating aspect of AI, because it gives you the exposure to everything, to the model deployment, to the hardware things, how they influence actually the execution time.
Okay. I think you can probably see the poll results. Pop those up. Thank you. So the answer, and I probably put my thumb on the scale here. PyTorch comes in at 52%, as it should, of course. But TensorFlow, no surprise to me. Is this what you expected to see as well, or is it distinct?
It's good to see TensorFlow still has its fans. If you think about Google, they are pushing JAX now more than TensorFlow. So yeah, it's good to see. But yeah, PyTorch is what we expected. Surprised to see Onyx a little low, but yeah.
We have a couple questions, and then one of which I think is going to be great for leading into the demo. A quick question. If you would like to create a personal general use assistant, which model should I use?
Shall I show the Llama CPP demo?
Well, I have a question following this. This is just a quick question, and then we'll go into
It can be used as a personal thing. So any of the Llama models are a good start. It's open source. It'll run on your laptop. And the Llama CPP project was created to run Llama model on your laptop. So that's a great place. But the good thing is Llama CPP and Ollama related projects, they allow you to run n number of models. You can run Gemma, you can run Alibaba Qwen. All of these are very good. They are from 0 to, like 8 billion model, easily runs on your laptop. You want fancy? People have run DeepSeek on cloud instances, on CPU instances, which basically means if you just take a single kind of EC2 instance or Google Axion instance, or even I think it's Intel AMD instances, you'll be able to run DeepSeek, the full model, the 650 billion model. So you'll see the whole, what is called the thought behind the inference, right? It'll show the steps of how it's thinking.
Then in this question, it's gold star to Joseph for asking a really wonderful question for me is, can you provide an example of a real world application where on edge device inference is happening using gliding? So what a great time for demo is to see it. So if, you have, I think, 2 demos to show us. So let's, whichever one you think shows that best first, and then we'll do the other one afterwards.
Should I start, Ashok?
Yeah, the mobile one will be real edge use case. Yeah.
Okay, so I'm gonna share my screen with audio. Okay, so let me see. I guess you can see my screen, right?
Yes.
Can you see? I can see. Yeah, I can see.
So this is our most recent demo that we accelerated through Clyde AI in collaboration with Stability AI. If you don't know Stability AI is behind with the most famous model for generating images, Stable Diffusion. And we had this collaboration to bring for the first time a model that is capable to generate audio samples from text in a very short time. And we're talking about around 7 seconds to generate roughly 11 seconds of audio. So this has been accelerated with Clyde AI using Executorch. And we have also a video. I'm gonna show now. Let me see if I can also. Yes, I can. So this is okay. Let me put it at the beginning. So the demo consists of a field where you can prompt the desired audio that you want to generate. For making super simple, we have some predefined audio text. Here is generating, and once it's generated, you will hear the audio sample. Let's see. And this is super cool because this runs entirely on the ARM CPU locally and it can run on wide range of mobile phones out there, not necessarily premium phones, but also it can work on mid-range phones as well. And this is, in my opinion, probably the most interesting project I have been working so far, because for the first time we managed to bring on mobile something very, very complicated like audio generation.
That's a pretty cool demo. Ashok, do you also have a demo? I'd like to, I'm now excited. Like, show me more, show me more.
Yeah, so let me show you a chatbot demo.
Okay.
So this is
Well, that's
hosted
coming
on
up. Let me
arm.com.
just, well, that's sorry, Ashok. There's a link in the chat for everybody that goes to the free ARM course. So to learn more, I just wanted to point that out while you brought the demo up. So check the chat. There's a link to the free course. But sorry, go ahead, Ashok.
So let's ask the question, which model shall I use for personal assistant? So this is Llama 8 billion model running on cloud instance. So, okay, this is 8 billion parameter limitation, I guess. So let me ask about, tell me more about. This is running on a cloud instance. This is not running on a GPU or anything of that sort. This is just running on a CPU. So there is 96 cores of them. I mean, you can easily run the same thing for a lower core count. But the interesting thing is we can do 55 tokens per second. If you saw the scroll, it is really fast. Usually 5 tokens per second is enough for real-time uh, effect for the end user. We can do 55. In other words, you can take the instance and run 10 users in parallel, right? So this can be used as a personal thing. So you can run this on your laptop and you can use it for your own use case and the data will not leave your laptop.
Which is always nice. So the running it on your laptop, your phone, there's been some questions about, is there one phone that's better than another phone? If I'm gonna get into the market, what should I be looking for? ARM, of course, but what is there a way of telling from the box? Like, how do I do a search if I really want to spend time with this?
So the question is, how do I know which phone to take for? Okay. If you're an Android app developer, you usually don't consider one phone only, right? So, and this is the story I was telling before, because your application has to run on several mobile phones out there. What I usually suggest, if you are considering to develop an app at scale, at least, you need to consider the worst case scenario. That will be if it runs there, it will run for sure everywhere. So that is my recommendation. If you start, of course, to take the best mobile phone out there, well, for sure it will run there, but I cannot guarantee it will work on other mobile phones, because if you want a mobile app, you probably need to consider the scale of your of deployment as well. And so this is my recommendation, actually.
Because approachability, I think a lot of people have a phone, and they may not have a massive laptop. So how do I get started locally if all I have is a phone? Which phone do I choose next if I want to spend time with this? Those are questions I would ask, because not all processors, not all architecture is the same. So understanding that. We have about 5 minutes left. So I can try to get a couple more questions from the chat area. Of course, you can also ask questions as well. So, Ashok, G, and Marco, if you're like, well, I have a question, well, we can always handle that as well. But a wide range of questions, one of which is that, well, it's a general question. Can you list and compare most relevant benefits of running inference in ARM and x86? In general, let's just do a general comparison. So for the next 4 minutes, if you were to compare and contrast, what would you say?
When we compare, I think if you do similar features, both CPUs have special things for ML, right? Intel has bfloat 16 support. We have bfloat 16 support. Intel has integer 8-bit support. We have integer 8-bit support. Intel has a vector unit. We have a vector unit. Intel recently brought something called AMX to accelerate bfloat 16 int8 operation. Recently, ARM brought in something called SME, right? So both CPUs are bringing in newer and newer features. I think the biggest contrast between ARM and Intel would be our journey to where we got. So we always started with energy efficiency as a primary goal. The reason is we started with mobile phone where there was no fans, right? It was not possible. We had to fit in those brick phones in ages. So typically, if you take a CPU for the same performance, usually ARM is more efficient because we have come with a journey where that's always been a number one goal more than the performance itself. So typically, if you use an ARM, you would end up spending less power, less energy for the same outcome. Okay, that's one way to look at it. The other difference would be is level of software maturity. So one of the things we do, uh, forefront, first thing is we always have decided that we will not have our own special software. We upstream it to open source, right? So there's no ARM PyTorch extension. So we don't have a special extension for PyTorch. We just straight put it into PyTorch. We straight put it into TensorFlow. We straight put it into Onyx. In the case of x86, sometimes I think it's to do with time it takes to some of these features upstreamed. You may need to use Intel PyTorch extension or Intel special software to get the best performance. So that's another difference we see in the company's strategy, how ARM approaches this problem and how Intel approaches this problem.
Sounds good.
Otherwise, CPUs are more or less, I think, even keeled when it comes to capabilities these days.
Okay. And I always love hearing open source. So
Yeah.
Clyde, I think you were saying before, Clyde is a Greek for key or opening of lock.
Correct. Correct.
It's the
Comes
key
from
to unlock AI, huh?
yeah, the key
You stole my
operator.
statement. Yes, exactly. It's the key to unlock AI, along with, of course, PyTorch, another amazing open source tool that is Linux Foundation. Well, this has been a great conversation. I've learned a lot, and thank you very much for your time today. Gianmarco, Ashok, not only thank you, is there any last minute things you'd like to say to the attendees?
Well, I mean, for me, it was a pleasure actually be here. What I hope is to see more people creating AI applications on CPU, because I hope with this presentation we have highlighted actually that CPU is more than an option for AI. In some cases, actually, it could be what it can unlock your application from a power and latency perspective.
Like any other AI practitioner, right? We are all there to help you. We couldn't answer some of your questions. Both of us are on LinkedIn. Please do connect. And if you have a question that we didn't answer that you wanted us to touch base, then do send it over there, right? Otherwise, it was great. We saw some nice poll results that makes us rethink maybe some strategies of projects we have like TensorFlow. But thank you.
What I can
Thank you so
also
much.
add is if you are new to CPU AI deployment, we have prepared quite a lot of what we call learning paths, which are tutorial. So if you're completely new, you can probably follow this tutorial to learn how to use maybe PyTorch, TensorFlow Lite, Llama.cpp, or Executorch, and are very, very, very good ways to learn and enter this interesting world.
Sounds great. Well, thank you again. Have a great day.
Thank
Thank
you.
you. Bye.
Thank you so much to our speakers for your time today, and thank you everyone for joining us. Just a quick reminder that this recording will be on the Linux Foundation's YouTube page later today. We hope you join us for future webinars. Have a wonderful day.